Okay, sounds like a performance, waiting until you get the okay. Well, thank you very much for putting this paper on the program. This is joint work, among others with Felix Fattinger, who are sitting there next to me, and a number of other people. I would just want to highlight Nitin Yadav, who is a postdoc in computer science in my lab and actually has worked on artificial intelligence for his PhD, and then Carsten Murawski, who is more of a neuroeconomist. This is also computer science, just like the previous paper, but a very different type of computer science. It's about computational complexity. And we started doing that when I was still at Caltech in around 2004 and 2005. So half of my presentation is just going to be a little bit give you of a background information as to what we are talking about here and how it relates to economic concept. Otherwise, you're not going to actually understand why we ran the experiments we did. All right, so I'll give you some background, complexity and uncertainty, and then two experiments with markets. So complexity and uncertainty. Look at these two problems. Definitely would call them events. They're in fact, for the computer scientists, decision problems. They're questions that have a yes or no answer. So the top one is a classical one for finance, for psychology, neuroscience, etc., animal learning. Somebody chose one of these two urns, the left or the right urn. The left urn has a majority red balls, and you don't know which one was chosen, and you have to basically bet on whether it was the left one or the right one. That's a classical learning environment. How do you learn? You actually sample from it, and over time you figure out which one is the right one. The bottom one is the so-called graph coloring problem. And the question here, the specific instance is, can you assign 5 colors to the vertices in this graph so no two vertices sharing the same edge have the same color, right? What's the answer? Question is, how do you learn about this? You can try randomly. So the whole point today will be that if you try this randomly, be my guest. It's extremely ineffective, right? So there's a type of machine learning out there, artificial intelligence, that's not working for this type of problem. All right, so that's one of the crucial points I want to make. By the way, the solution to the second one is, the answer is yes. All right, so and here's the example. The colors blue, yellow, red, and black. All right, so the answer happens to be yes. You could have guessed that, of course. So let me now step back and talk about decision theory, hardcore decision theory. How do we teach decision theory, classical decision theory, as opposed to what the computer scientists have been looking at? First, there is choice, and second, there is learning. Of course, in standard decision theory, we don't distinguish between the two in these two, but you have to distinguish under computational complexity. So a choice is, for instance, do you want to bet? Whether the answer is yes. Do you want to bet or not? Right? So for the choice to be consistent, that is, for your choice to be rational over time across all the possible bets, you follow Savage's prescriptions, and you basically become an expected utility maximizer. And you use arbitrary priors. It doesn't matter which priors you use. You just use arbitrary priors, and maybe you update using Bayes' law. And that's true for both cases, right? The Savage theory is generic for uncertainty here. Learning is a different matter. The standard way to learn, and this comes also from animal learning, we know that, sampling. You just sample, and you may do important sampling. That is, you can use your prior to become more informed about what you're going to do, but it's still random sampling. That's very effective in the urn case. And what's really important is, and that distinguishes you from the graph coloring problem, is that the residual uncertainty can be quantified precisely. That is, at any moment in time, you can say that's the probability that I'm more than epsilon away from the truth. The machine learning people call this probably approximately correct, right? It's extremely ineffective in the graph coloring case. And the residual uncertainty cannot be quantified, right? Kolmogorov would just actually say, there is no law of large numbers, so don't use my theory, right? But of course, we have this tendency to always use Kolmogorov's theory. And Kolmogorov says, no, this is a domain of finite mathematics. There are better approaches that search the solution space systematically. More background, computational complexity. So the graph coloring decision problem is an example of a computational hard problem. And intuitively, what this really means is there does not exist, and I should say, there does not exist yet a learning protocol algorithm that guarantees convergence to the true answer in polynomial time. They're all exponential, right? So if you increase the number of nodes, you increase the number of colors that you decrease the number of colors that you can have, or increase it, it becomes exponential, and very, very quickly. You need an enormous amount of time. Compared to the ERM problem, the convergence is at the square root of the sampling size, right? All our central limit theorems, including GMM was mentioned before, square root of t. T is the sample size. What are algorithms, right? So there are two types of algorithms. There are algorithms that find a solution, right? So we do not know for these problems any algorithm that actually can do this in polynomial time, they're exponential time. There are polynomial time approximation algorithms that are used to fill, for instance, container ships in the town that I grew up in Antwerp, in Belgium. Right? I'll come back to approximation algorithms because I'm going to look at humans. Little history. In the early 20th century, mathematicians like Alonzo Church, Alan Turing, they discover complexity. Hilbert, you all know Hilbert spaces, right? Basis of mathematical finance and of quantum computing. You all know Hilbert spaces. Hilbert claimed that everything you can write down in an equation can be solved. And then Alan Turing said that's not right. Friedrich Hayek, an economist, 1945, a fantastic article that I never understood until actually you start getting into computational complexity. So this is a paper about a claim, a conjecture that markets help spread knowledge in society when this knowledge cannot enter into statistics. This is literally taken from his paper. There are not supposed to be any statistics in that paper. And all the follow-up, of course, we're talking about Grossman, Stiglitz, Verrecchia, Diamond, all those guys use statistics. And they refer to this paper. Unfortunately, that's not what the paper is about. That does not mean that Grossman, Stiglitz, and all these guys are wrong. They're right. And it's fantastic. We have learned an enormous amount of stuff. But that's not what Hayek wanted to talk about. In the late 20th century, computer scientists developed these solution algorithms, both the ones that actually are will get you to the solution, like using dynamic programming, but they're exponential, or approximation algorithms. This is not machine learning. This is a very different type of computer science, right? In the early 21st century, computer science helps understand human choice and learning under complexity, both individually and in markets. That's we. That's us, right? So we have been doing this since 2005, and I'll say a little bit. Most of this is published. Actually, everything is published in the science and engineering or computer science literature. So we're going to focus today on the 0-1 abstract problem, not the graph coloring problem. Why? Because it actually is the canonical problem in economics. It's maximizing utility subject to a budget constraint. And there are indivisibilities. The indivisibilities makes it very hard. This is actually the interface we have been using. You can see ULeaf here. Actually, this was developed when I was at University of Utah. Right? It's still, they still own the game. So you have a number of items. Each of these items have a weight, 140 kilograms, and some value, let's say 127 euros here. And then you have a knapsack with a maximum capacity at 1,300 kilograms. What you want to do is pick the right items here that maximize the value of this knapsack. This is deceptively simple. You know, this particular instance, you know, about 60% of the time people get it right. They take usually 3 to 4 minutes, and then they submit it. They won't take more time than that. Very much in a nutshell, we have at least 7 or 8 publications on this, but I'm going to focus on a few things about how humans behave here. So this is based on our scientific reports paper and one for in artificial intelligence. So first, theoretical instance complexity predicts human performance. So what the computer scientists have thought about what complexity is for a Turing machine, for an abstract computer, works for your brain too, and your brain is not a Turing machine, right? We do not work like computers, right? And as you know, I work on brains, right? So, second, humans spend more effort on more difficult instances. This is for an economist completely crazy. Why would you do that, right? It's like you take an exam and you kind of spend not enough time on the easy problems and a lot of time on the difficult problems. Do it the opposite. For today's talk, the next 2 points are important. Humans use approximation algorithms. They do not find a solution in general, and in fact actually don't know how far they are from the actual solution. And they cannot quantify it because there is no way to quantify it. including, for easy instances, the greedy algorithm. The greedy algorithm is, if you start thinking about it, you're not going to randomly try out things. What you're going to do is you're going to order these items by value over weight, 144 euros over 137. And then you first put in there the item with the biggest bang for your buck. And then you go all the way until capacity, and that's my solution. It can be shown that this algorithm can be arbitrarily bad, right? So it's a bad approximation algorithm. Don't use it, right? But anyway, humans actually very often start with that. However, when the instance is actually difficult, they don't start with it, which of course raises the issue. How the hell can they figure out whether this is difficult? Because the measure of instance complexity is something you cannot compute until you have the solution. This is completely paradoxical. You know, that's why we go to conferences on artificial intelligence, because these guys are interested in that, right? Second, humans visit a small fraction of the solution space, but collectively they visit a very large fraction, and that's what I'm going to talk about today. How do you now actually get these people, bring these people together, and let them talk to each other? And as economists, if I may call myself sometimes an economist, we don't believe people will ever talk to each other, right? Certainly when they can make money on the knowledge they have. So how can we harness collective intelligence to spread knowledge in society? And this is the title of Hayek's 1945 paper. The title is not how to spread information, but knowledge, solutions to these complex problems. By the way, all the math I'm talking about was not invented yet or discovered when Hayek wrote this. It is absolutely amazing when you read this article. So Hayek's solution is markets. And so, I'm an experimentalist. Let's try this, right? So with Deborah Miloso and Yadav at Caltech, we ran the following experiment. We actually compared markets with a standard economic incentive mechanism, which is a price system. The price system is very simple. We had 60 US dollars, and the first to submit a correct solution to one of the knapsack instances we gave them gets the $60. This was at Caltech. Caltech undergraduates are poor. Within 10 minutes, they could make $60, so that's actually fantastic. Then we had a treatment where we had a market, right? So you all know we can set up markets online. They are just work with an open book system. And what we did is we introduced, being asset pricing theorists, a complete set of markets. That is, we have digital options for each of the items, and that digital option paid out $1 if it was in the optimal solution and 0 otherwise. So we had 10 markets because we had 10 items. At one point we had 12 markets because there's 12 items, but that's just a little detail. So Grossman 1981 will tell you that with a complete set of markets, even under under noisy rational expectations, you get generically the full revelation of information. But of course, that's using probability theory, not using complexity theory. We have random initial allocations, and we use the 60 US dollars to pay the liquidating dividends on all these options because it has to come out of our pocket. You can make money only by trading here. So you can imagine, right? Typical economists would say nothing's going to happen, right? There is no reason to trade here because, if I start trading, is selling a particular security, unfortunately, Sean being an extremely smart guy, he's going to pick that up and he's going to, steal my knowledge. Right? So there's no collaboration in either mechanism. We published this in Science 2009. And here is just the key takeaway from this. These markets actually do better than the price system. So the percentage of people who find the optimal solution is higher than under the price system. So it's really like Hayek predicted or conjectured in the spread of knowledge in society. Fantastic, but then the question is why, right? And can we improve? So we replicate this in Melbourne. There was a conference of the Society of Experimental Finance the last 2 days. This is my second conference this week. And one of the complaints among the non-experimentalists was, well, you use Caltech students, right? They're extremely smart. Well, let's use normal people, Australians. Actually, as you probably must have read, about 50% of them are Chinese, right? So it's really a world cross-section of the world population, maybe an overweight on the Australians. So here's actually what happens in prices. This is time. They trade for about 10 minutes. And each of these lines are the trade prices or the prices at which each of these securities treated. For instance, here is a 184.28 item, and it happened to be in the optimal solution. So it had a weight of 28 and a value of 184. And as you can see, it goes up. This is what you want, right? Right? Here's an out security, the price went down. But what's so remarkable is it's incredibly noisy. This blue here one that happened to be out, for a while people thought it's got to be in. No, it's not in. Yes, it's in. Right? This is very typical. This is very different from when you run an experiment, the same experiment with urns, with 10 urns. Dramatically different. Second, informativeness. So here you can see this is the performance score. First, the blue lines of the individuals. So you can clearly see, you do better than random, 50% solutions. But the about 75% of the time, individuals in this experiment actually find the solution. Hey, these are simple problems. No, they're not simple. All right. So these, now we actually stratify everything by complexity. There's a measure of complexity that we started using already in the science paper, the Sonic K. I don't have to explain what this is. This is really complicated. But it requires you to know the solution. As you can see, when it becomes harder for a computer to find a solution because it has to work more, it has to do more calculations, the performance of humans goes down. Right? Actually, the red ones are the humans. The blue ones are the markets, the market prices. So what you do is, you're an economist, you try to read information from the prices, you construct a knapsack and you see what the percentage of time is that they're right. And you can see markets do uniformly worse than the individuals, than the average. Well, that's also what Grossman and Stiglitz would predict under a noisy rational expectations model. So you would say, well, that's fantastic because we don't have to learn computational complexity in order to understand markets when when the uncertainty is generated by computational complexity as opposed to drawing balls from an urn. Information transmission, so one of the questions we ask is how do people learn more? Is it because in the price system, the best person actually, best person only the best person can earn the $60, whereas in the market system, even if you're mediocre, maybe you can pick up some money? Or is it because they actually read information from the prices? And this plot, I'm not going to explain the details of it, really shows you that they actually revise the items that are in the optimal, in their solution when when the prices are low and the volume is high. So it's not only price, it's actually volume that's extremely important. So they get cues from the market to reconsider everything. Now, experiment 2. So that's when Felix comes on board, and Felix looks at this and says, I am not impressed, right? So he's not impressed by this. He wants to do much better. So we then actually started thinking about computer science again. Can we do better? So we go now to the approximation algorithms. I already mentioned humans use approximation algorithms. These algorithms stop searching based on an internal criterion. Right? So they try out a few things and they stop depending on those specific non-random trials. Switch gears, let's talk about oracles. 10 minutes, okay. Oracles. Oracles is a concept in computer science that is a very strange thing when you first see it. It is actually like the oracles in Delphi in Greece. The Greek went to Delphi before they started to fight a Persian or something like that, to ask the oracle there what they should be doing in order to beat the Persians. And then the oracle would say something completely crazy, but always correct. It was just a question of interpreting it correctly. So what's an oracle for the computer scientist? It's an exogenous message passed on to the algorithm at a particular point in time that actually makes the problem easy. So the computer science question is, which oracles make the 0-1 knapsack problem, for instance, or the graph coloring problem, polynomial time solvable? And then, of course, if you can find it or that message passing, then maybe you set up a mechanism that actually becomes an oracle. We are not going to try to make the 0-1 knapsack polynomial time solvable. We're going to actually make it because actually humans don't solve these problems, right? We need an oracle that actually helps the approximation algorithms. So our question is, can you find an oracle that makes an approximation algorithm better, faster, more successful? So it's kind of a new form of mechanism design in economics, where you now think about markets or mechanisms as providing crucial information for people to solve their problems, their difficult problems. Exactly as it was proposed in Hayek's paper in 1945. I'm almost literally quoting from the paper. So the question is, can the market be an oracle? The oracle actually has to be exogenous to the algorithm. The algorithm here is a human. The market, of course, is composed of the humans, and so you wonder maybe this can't happen. But don't forget, we're talking about competitive markets. Right? The oracle has to be exogenous. It's not influenced by an algorithm. In competitive markets, the individuals do not have any impact on the price, and we know from our experiments when you have about 10 people in there, you can take a guy out there and not change at all the prices. So then the question is, which market is an effective oracle? Which message is to be passed on to the participant? So what we decided to do is to have one market only, not 10 markets, not 12 markets. And it has a security that pays the value of the optimal solution. So now you can trade a security that bets what the optimal solution, the value is of the optimal solution. It's a highly incomplete market in the traditional sense of completeness. It does not reduce the complexity of an abstract problem. This world is extremely strange. Even if I tell you the optimal solution to the first problem I showed you was 450 euros, you would still need more than polynomial time to figure out what the items are that go in there, right? So that's not changing the complexity. However, it could provide crucial information for approximation algorithms, an external benchmark of which to decide whether to continue search, right? So you see that the price in the market is $500 and you're at $400. You say, well, maybe I should search. But of course, there are people who bluff in the market, right? This is a hugely incomplete market, so according to traditional asset pricing theory, this will fail, right? Well, you know, I'm an experimentalist, I'll just try it, right? But don't forget, this is designed with the theory in mind, right? That's the real important thing. This is not just an experiment, well, let's just try this, right? It is actually using computer science in order to think about markets. If you think of companies as knapsacks of projects, the security we propose can be thought of as equity, and at the end I'll say something about a historical antecedent to what we're doing. So questions, can markets generate such an oracle? Maybe we'll see bubbles. If you talk to a typical experimental finance person and you ask, do you see bubbles in markets? And they will say, yeah, the mispricing is all over, but that's because most of these guys work with a particular paradigm, the Smith-Suchenick-Williams paradigm. This is going to be a beautiful counterexample today. Will participants trust the market? You can look at a bid-ask spread and see how small it is to get some ideas to whether people trust things. Will participants be able to use the price signal to increase their chances of finding the optimum? The answer will be yes. So very quickly, here are the results. This is for 3 sessions. Here's a difficulty, 1, 3, 2, 0. 0 is easy. That's actually the greedy algorithm works here. 4 is unbelievably difficult. This is not the spread, this is the price. Here is the true value, the optimal solution. You can see this is sin k equals 1, the price zooms to there, right? So that's the kind of a medium difficulty. Very difficult, you get actually very close to the solution. So these prices are extremely reliable. Do the participants in the market know that? No, we know that, right? And there's this, do people trust this? Well, actually, let me say something more about the prices, because this actually violates also Grossman's prediction. So here is, for one market, the optimal solution. Here is the average value of the solution submitted by the participants, and here's the market price. The market now does better than the average person. That's not to come out of our noisy rational expectations model. They all predict exactly the opposite, right? The average trader does better than the market, right? Here, the market is better than the average trader. Right? Trust, bid-ask spread. So that gives you actually some idea as to what the bid-ask spread is in the beginning, and then after about 10 minutes. Right? And you can see in every case, even when it's unbelievably difficult, right? The bid-ask spread goes pretty much to a tick size. There's a lot of trade, there's a lot of enthusiasm, people are working hard, and I'll explain in a little bit how they work. What's also striking about this is the following, right? The spread, if you go from sonic A equals to 0 to sonic A equals to 4, you see the initial spread increases. So you can put a line in there. When sonic A is 4, when this problem is extremely difficult, the bit-out spread is higher. You ask yourself the question, how does the market know this? Because I don't know this number until I've solved the problem. Right? Which is, of course, again, as I said, that's why artificial intelligence people are really interested in these results. Markets sense difficulty. If you were to be able to, when a container ship comes in the harbor in Antwerp, and if beforehand you could say, this is a very difficult one, use that algorithm as opposed to the greedy algorithm, they would win. They would actually save an enormous amount of time. All right. Knowledge spreads more effectively. Right, so this is the complete markets, the first experiment, and you can see, as a function of sonic K, you can see that the percentage of people who actually find the optimal solution goes down. In the single market, that is our Oracle market, it's much higher, as you can see. There's one exception here, but that has to do with multiplicity of solutions. Right? Just to give you an idea what world we live, we compare this to random sampling. So you're a savage agent. Machine learning. This is machine learning, the performance of machine learning. And what we impose is that you are allowed to sample as many times as our individuals do. That is, we count the number of full knapsacks they get at, and now our random sampling algorithm is allowed to use exactly the same number of samples. Right? And as you can see, this is the multiple. You can see, it's pretty dismal. That's why people who have to fill container ships are not using machine learning. All right? Prices induce search, and search induces pricing. I'm not going to go through the details here, but you can clearly see this interaction. Guys that are behind because their value is lower, they try again. They don't stop. Right? And if they don't find any better solution, they submit asks. Beautiful results like that, this interaction between individuals and the markets. You can see this dynamically at work. I said there is a historical antecedent to this. So when we published our science paper, the economic historians, in particular Nuvolari, came to us and said, oh yeah, this mechanism sounds very much like what they had in Cornwall. Steam engines, steam pumping engines for markets. This was after James Watt's patent on the steam engine was expiring. During the 30 years of the patent, there was no improvement of the steam engine at all. The capacity was exactly the same, 30 years. Thank you. When the steam engine went off patent, they decided in Cornwall to set up the experiment I just explained, the second experiment. Not exactly the same detail, but pretty much the same thing. And you see the effect on the performance of the machines. It doubled within 10 years. 10 years, doubled, right? That tells you a little bit about how to organize real life. So conclusion on the computational complexity, sample is an ineffective way to learn, and humans appear to understand this. Humans collectively visit a large part of the solution space, so harnessing collective wisdom requires the right transmission mechanism. Hayek conjectures that it's markets. Contrary to classical asset pricing theory, incomplete markets may cope better with computational complexity than complete markets. That's it. Thank you.